All right, in this video, we'll be introducing the derivative. Last time we finished our first major topic of limits and continuity, and we are now ready to come back to an idea from limits that we talked about before with the slope of a tangent line and how we use the slope of the secant lines to help approximate the slope of the tangent line with a limit process, and we'll formally define that process to help us find something called the derivative. So first, in our objectives here, we're going to answer conceptual questions involving tangent lines and derivatives. Then we'll use limit definitions to find equations of tangent lines. Then we'll use limit definitions to evaluate derivatives at given points. Then we'll complete average and instantaneous rates of change from graphs and tables. And then we're going to find functions from the limits of difference quotients. We're going to find derivatives specifically from the limits of difference quotients. So those answers there will be a slope generating function called a derivative. All right, so we can let's go back and look at this from before with our example that we had previously when we talked about limits, that we had this curve f of x here, and we had a point over here that we called a f of a, and we had this line here that we were interested in. This red line is called the tangent line. I'm not doing a great job drawing it. Here, I'll actually do better if I put a f of a over on this side because I do better with drawing to the right. There we go. It's a little better. There's my tangent line that I'm interested in. And we have these, well, it's not much better, but you get the idea that it just touches the curve there and has the same slope at that point. And so we're going to have this process where we approximated the slope of that red tangent line by picking some points that were close to it, maybe like here, getting a secant line that was like so, and then getting a secant line that maybe was a little closer to it, like this. Go with dark purple here. Maybe that was a lot closer to the slope of the tangent line there, and so on. So we just picked different points and we used a limit process to say that the right answer here was between this kind of magenta line and this purple line, because the purple line's slope was too big and the magenta line was too small, something like that. And so we squeezed in until we got something that was just right. So we had a formula that the slope of a secant line could be given by the average rate of change formula, f of b minus f of a over b minus a, or that could be given as y2 minus y1 over x2 minus x1, something like that. The slope of the tangent line, since we only have a single point, we talked about was the limit as h goes to 0 of f of a plus h minus f of a divided by h. This thing here that we're taking the limit of is called a difference quotient. And you dealt with those a bit in pre-calculus, and we'll I'll write that right here. Limit as h goes to 0 of f of b minus f of a over b minus a. Let b equal to a plus h here. So this is going to be equal to limit as h goes to 0 of a plus h minus f of a over h. Write that in there. That's what the slope of our tangent line is going to be. And that's going to be our main thing that we're going to work with in this video here. So let's go ahead and define, let's get the derivation of the limit definition of the derivative. So recall we have learned the concept of a limit. So based on the graph above, we could use a limit to derive the slope of the tangent line. Again, saying that our slope of our secant line is equal to f of b minus f of a over b minus a. And then taking a limit as b approaches a or as h which approaches 0 where b is equal to a plus h. H is the distance between x equals a and x equals b, which we know b is going to equal to a plus h. We obtain the limit definition of the derivative to be, this is our new notation for a derivative, f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a divided by h. The limit definition of the derivative at a specific given point, x equals a. So notice this is going to give me a number. This is not going to give me f prime of x that we'll be interested in later. This is the limit definition of the derivative at a specific given point x equals a. Right? If we want the limit definition of the derivative not at a specific point, then we want f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And this is going to be the one that we're going to be using most often. This is going to give us the function that we were talking about before, a slope generating function. To find the slope of any point on the curve. All right. Our problem statement for the first type of problem here would be something like use the, it might say limit definition, but it'll definitely say the word definition of the derivative something, something, something. When it says to use the definition, that's the keyword there. You're going to need to use the limit definition of the derivative, either definition number 1 here. This is usually definition number 1, and this is usually definition number 2. Whether you want to find f prime of x and find this slope generating function here, or whether you want to find the alternate definition, which gives you the slope at a particular point, use the limit definition there. So let's do some examples here where we use the limit definition of the derivative to find f prime of x. For f of x is equal to x squared. Notice that we were not given a specific value to find the slope at, so we're using definition number 1, the generic definition, that f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. So remember that, as an aside here, x plus h squared is equal to x plus h times x plus h. It's going to be equal to x squared plus xh plus hx plus h squared is x squared plus, and pick your favorite order here, whether you like xh or hx better, but there's 2 of them because multiplication is commutative, plus h squared. So we're going to make that substitution now for f of x plus h, because this equals f of x plus h. F prime of x is equal to limit as h goes to 0 of x squared plus 2xh plus h squared minus the original x squared over h. X squared minus x squared gives me a 0. This is limit as h goes to 0 of 2xh plus h squared over h. I'm going to factor the numerator. You could also split it up. I'll show you both ways here. Factor numerator or split fractions. Limit as h goes to 0 of h times 2x plus h, just pulling out the greatest common factor there. H's will cancel and leave me with limit as h goes to 0 of 2x plus h. Now that that discontinuity is removed, I can go ahead and use direct substitution. 2x plus 0 is 2x. So f prime of x is 2x here. If I want to split the fractions instead, I have 2xh over h plus h squared over h, and h divides out with h to leave me with 2x. H goes into h squared h times, and then I have 2x plus 0 is 2x, and again, this is what f prime of x is equal to. Either way, you get the same answer. So now we have example 2 here. F of x is equal to x cubed minus x. Probably don't have Pascal's triangle memorized, but I'll show it to you. But this shows us the coefficient pattern for a plus b to the n, or like x plus h to the nth power. So we see that we had 1, 2, 1 here for squaring. This is when n equals 2. This is n equals 1. This is n equals 0 for that row. This is n equals 3. I'm going to have 1. Let's just write this. X plus h cubed. It's going to be 1x cubed plus 3, and then take an x out and add an h in, so that there's always 3 variables, plus 3, take an x out, put an h in, plus 1, take an x out, all the x's are gone, and we have all h's left. So this is x cubed plus 3x squared h plus 3x h squared plus h cubed. If you need to go higher powers than this, you can continue Pascal's triangle by putting ones on the outside, then adding 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and just put those sums in between numbers. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and so on, and this will stay symmetric right down the middle here. This is really useful in statistics and something called combinatorics in discrete math to find something called combinations. Not a huge deal to you other than we have something called the binomial theorem, which is where I need these coefficients for to do this binomial expansion like this. So my f of x plus h here is going to be this piece minus x plus h. So let's see if we can simplify that at all. I don't have any plain old x's or h's over here. So this is going to be x cubed plus 3x squared h plus 3x h squared plus h cubed minus x minus h. So there's my f of x plus h aside. Now I want the limit as h goes to 0 of f of x plus h minus my original f of x, all divided by h. It's going to be the limit as h goes to 0 of x cubed plus 3x squared h plus 3x h squared. Actually, I'm going to need a lot more room, so let's not try and write that on the same line. Let's come down a line as h goes to 0 of cubed plus 3x squared h plus 3x h squared plus h cubed minus x minus h. And then we have minus x cubed plus x because we subtract the original by changing the signs and adding. And that will make x cubed minus x cubed is 0. And then negative x plus x is a 0. All my terms without h have dropped out. I have limit as h approaches 0, 3x squared h plus 3x h squared plus h cubed minus h over h. And there we are. All right. Now let's go ahead and factor. Use either technique that you like here better. I've shown you both. They're equivalent. But I like the greatest common factor technique better. Then anything that has an h left in it will be going to 0. making f prime of x equal to 3x squared minus 1. Right? Moving right along here to f of x is equal to the square root of x. We're going to have to use a technique here where we're going to rationalize the numerator. So we're going to have limit as h approaches 0 of square root of x plus h minus the square root of x over h. So normally we rationalize denominators in math, but now we're going to need to rationalize the numerator and multiply them by square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. This is going to take advantage of the difference of two squares formula, that if I have the same thing with opposite signs here, it has to be the difference of squares, and squaring those square roots is going to make the square roots go away in the numerator. Do not distribute in the denominator, leave it factored. And so this is going to be the square root of x plus h squared minus the square root of x squared, because it's a minus b times a plus b. So that's the limit as h goes to 0, x plus h minus x over h times root x plus h plus root x. X minus x is 0. And we get limit as h goes to 0, h over h times root x plus h plus root x. This is why I said to leave it factored, so that those h's will cancel there. And you have limit as h goes to 0 of 1 over root x plus h plus root x is 1 over root x plus root x is 1 over 2 root x. And I don't think that you need to bother to simplify that at all unless your instructor tells you to rationalize that denominator when you're done. You're going for a numerical answer for f prime of x when you're done. So it'll be simpler for you to leave that there if x is a perfect square. Right? The derivative of a function at a point. Definition, the derivative of f at x equals a, denoted f prime of a, is given by either of the two following limits, provided that the limits exist and x equals a is in the domain of f. So we can take f prime of a is equal to limit as x approaches a of f of x minus f of a over x minus a. This is typically the version of the second rule that I know from the textbook, or we already defined it earlier as limit as h approaches 0 of f of a plus h minus f of a over h. They're equivalent forms because we have defined a to, or x to be equal to a plus h here, basically. So if f prime of x exists, we say that f is differentiable at a. So x equals a is a given value. That's really important. You have to be given x equals a to be able to use this. If you are not given, x equals a, find f prime of x in general with the techniques that we just talked about earlier, using this function here. F prime of x is equal to limit as h goes to 0 of f of x plus h minus f of x divided by h. Okay. Let's look at some examples here where we're going to be given a values. So let f of x be equal to the square root of 2x plus 1. And we're told to compute f prime of 2. There's our a value. A equals 2. And we're going to use the limit definition of the derivative. So f prime of a is going to be, take your pick here. If you want to, I'm going to do it both ways here. Limit as a approaches 2 of f of x minus f of a over x minus a. I'm going to start with this one and show you that it's the same as the other way that we've been doing this. So limit as a approaches 2 of, sorry, as x approaches 2. There we go. There we go. So this is going to be square root of 2x plus 1 minus, and if I stick 2 in there, 2 times 2 is 4. Square root of 4 is 2. 2 plus 1 is 3. It's minus 3 over x minus 2. So this right now is limit as x approaches 2 of root 2x, and then minus 2 over x minus 2 is going to be something I want to rationalize this numerator. Plus 2, 2x plus 2. It's going to be limit as x approaches 2 of 2x minus 4 over x minus 2 times root 2x plus 2. And this is limit as x approaches 2 of 2 times x minus 2 over x minus 2 times root 2x plus 2. Those will cancel and leave me with 2 over root 4 plus 2 is 2 over 2 plus 2 is 2 over 4 is 1/2. Now let's see, I think I have some space to do this the other way. Not really. Let's come up here. So if I have limit as h approaches 0 of f of 2 plus h minus f of 2 over h, we'll get square root of 2 times 2 plus h plus 1 minus square root of 2 times 2 plus 1 over h, and I need limit as h goes to 0. It's equal to square root 4 plus 2h plus 1 minus 2 plus 1. Again, this is a limit. So h goes to 0. It's equal to root 4 plus 2h. 1 minus 3 is a negative 2 over h. And then we're going to have to multiply top and bottom by the conjugate. 4 plus 2h plus 2, root 4 plus 2h plus 2 is limit as h goes to 0 of 4 plus 2h minus 4 over h times root 4 plus 2h and plus 2 is going to be limit as h goes to 0 of 2h over h times root 4 plus 2h plus 2. H's will cancel, This is 2 over root 4 is 2 plus 2 is 2 over 4 is also 1/2, and I get the same answer both ways using either definition here. So now that we've learned a formula for the derivative, let's go back a step and say why exactly or what exactly does the derivative represent? And that's going to be the slope of the tangent line. So the derivative of f of x at a specific point x equals a is the slope of the tangent line to f of x at x equals a. So the value of the derivative of a function f of x at a point x equals a is the slope of the tangent line to the graph of f of x at x equals a. There's our definition. Thus, the derivative can give us information about the slope of a function f of x. So let's look at a slightly different function than we had before. Let's look at this parabola like this, crosses the x-axis twice, and we're interested, we may have talked about this before, we're definitely going to be interested in that tangent line right there that's horizontal. This is a horizontal tangent line. And the slope here equals 0. So that means that f prime of x will equal 0 for this point. And we know that this is a turning point on the graph. That is going to give us, in this case, a maximum point. It could also give us a local minimum. It could be another type of special turning point that isn't going to give us a minimum or maximum. But we do know that if we're on this side over here, that f prime of x, the slope here is positive. And we know that if we're over here somewhere, that f prime of x is negative. So we're decreasing over here. We're increasing over here. And somewhere between increasing and decreasing is this 0 point that we're interested in. And that's possibly going to give us an extreme value. That really looks forward to our applications of derivatives that are coming up, especially in this class where we want to maximize revenue and maximize profit and minimize cost and all these things. We will be using derivatives to help us do that. So a negative value for the derivative means that the function is decreasing. Positive value for the derivative means that the function is increasing. The average rate of change in f on the interval a to a plus h, where we just really have our good old b that we used to have here. We've called that a plus h, is the slope of the corresponding secant line, where we used to use f of b minus f of a over b minus a. And now we're going to call that f of a plus h minus f of a over h. It's the same thing as f of b minus f of a over b minus a, where we let b be equal to a plus h. So the instantaneous rate of change in f at x equals a is the slope of the corresponding tangent line at a f of a, provided that that limit exists and is slope of the tangent line is limit as h goes to 0 of f of a plus h minus f of a over h, or you could say that it's the limit as x goes to this a value of f of x minus f of a over x minus a. It's the same thing. So consider the function f of x is equal to x cubed plus 4x. Find the average rate of change of f of x on the interval 0 to 4, and then on 0 to 2, and then on 0 to 1. Well, we can just find some f of x things here. So f of x, we have 0, 2, and 4. If I stick 0 in there, I get 0. 8 plus 8 is 16 for f of 2, and 64 plus 16 is 80 for f of 4. And then I forgot to include 1 here. 1 plus 4 is 5. I've got 0, 0. Like I said, x, f of x. Okay. So we're going to need our average rate of change. First part, so f of 4 minus f of 0 over 4 minus 0 is going to be 80 minus 0 over 4 is 80 over 4 is 20. And then on 0, 4, on 0, 2, we have f of 2 minus f of 0 over 2 minus 0 is 16 minus 0 over 2. 16 over 2 is 8. And then on 0, 1, we have f of 1 minus f of 0 over 1 minus 0 is 5 minus 0 over 1. 5 over 1 is 5. So what are the equations of the corresponding secant lines? So let's go ahead and always use that 0.00 that's on the line. That's the easiest one to use since it's the y-intercept. So our first one here on 0, 4, that secant line has a slope of 20. So y equals 20x plus 0 for the y-intercept is 20x. On 0, 2, y equals 8x plus it has a y-intercept of 0. So that's going to be 8x. And on 0, 1, y equals, we had a slope of 5x plus a y-intercept of 0 is just plain old 5x. Let's find the instantaneous rate of change at 0, 0 on the corresponding equation of that tangent line. So for part C here, let's just go ahead and put it up here. Limit as h approaches 0 of f of x plus h minus, let's see here, 0 plus h minus f of 0 over h, like so. And limit as h approaches 0 of f of h minus f of 0 over h. And my function here, recall, was f of x is equal to x cubed plus 4x. So this is limit as h goes to 0 of h cubed plus 4h minus 0 over h is limit as h goes to 0 of h cubed plus 4h over h is limit as h goes to 0 h times h squared plus 4 over h. H's will cancel, but leaves me with limit as h goes to 0 of h squared plus 4 is 0 plus 4 is 4 for part C. So that's my instantaneous rate of change. So my slope of my tangent line is equal to 4. I'm going to have a point 0, 0. That is my point of tangency. So I'm going to have y equals 4x plus my y-intercept of 0 is 4x. And I can see that my slopes here were tending towards my tangent, my slope of my tangent line for D. So if I look at that that chart there, I can see that on the interval here, 0 to 4, then on the interval 0 to 2, on the interval 0 to 1, slope of my secant line as h was getting closer and closer to 0 as I come down here. The slope of my secant line was approaching my slope of my tangent line, which was 4 as I come down this way. All right, so that's it. If you want to actually put these equations into a graphing calculator or something like Desmos, you'll actually see those tangent lines or those secant lines rotating and approaching the equation of the tangent line. The secant lines will approach the tangent line as h gets closer and closer to 0. So that's it for these notes. Next time we will come back and talk about the derivative as a function. So see you for the next video.